Hello all, in today's session we are going to discuss about the small dipole and its analytical treatment. A small dipole is a dipole whose length is greater than lambda by 50 but less than or equal to lambda by 10 will be called as a small dipole. Now whenever we are talking about the small dipole, we must understand what kind of the current distribution is there on the dipole. So whenever we are talking about the current distribution, let us, this is nothing but the current waveform which is having the wavelength of lambda. So when we are talking about the small dipole, we say that its length is less than or equal to lambda by 10. So here this will be the lambda by 2, this complete wavelength will be the lambda, this will be the lambda by 2, half of this will be the lambda by 4, again half of this will be nothing but the lambda by 8, and somewhere here you will find this is nothing but the lambda by 10. So if we are talking about the current distribution in the small dipole, you can see this is nothing but the triangular in a nature. So current distribution on you can say your dipole will be the triangular in nature. So here current distribution will be triangular in nature. So we are going to assume something. So here, as we have assumed in the infinitesimal dipoles, or our assumptions for this particular analysis will be like this. So whenever we are talking about the small dipole, the first assumption is nothing but the small dipole is placed along with the, you can say this dipole is placed along z axis with center, you can say with the center of dipole at origin. This is our first assumption. The second assumption is that your medium surrounding to this particular dipole is nothing but the air. The third assumption is the diameter of this particular wire, you can say diameter d is very small than lambda. This is our third assumption. And the fourth assumption, the current is fed at the center of the dipole. So you can say current is fed at the center of dipole, and this current is fed using the transmission line. Now fifth assumption is that the current distribution is assumed to be triangular, as we have already discussed why it is assumed to be a triangular, as it is its length is very less than, you can say, the lambda by 10. The current distribution assumed to be triangular with the maximum value of I0 at the center. So current maximum value is I0 at the center, and it decreases linearly to the 0 at the ends of the dipole. So here, if we are interested in writing the expression for this particular current, as the assumption is that the current is triangular in shape and you are having the maximum current at the center and it is decreasing linearly to the 0 value at the ends of the dipole, your current equation will be this one. So I is equal to I0 1 minus 2 by L Z dash a z bar for 0 is less than equal to z dash L by 2. And the next one is nothing but, let us say this particular equation is nothing but the equation number 1. The second, I dash is equal to I0 1 plus 2 by L z dash a z bar for minus L by 2 z dash less than or equal to 0, and let us assume this is nothing but the equation number 2. So these are nothing but the expressions for the, you can say, the current distribution. So the small dipole and the current distribution can be shown like this. Suppose this is the z axis, so here this is z axis, I am assuming this is nothing but the y axis, and this is nothing but the x axis. So we have assumed that our antenna is nothing but the small dipole antenna, and which is placed like this here along with the z axis. So this is our antenna, and again I can say this is nothing but the antenna. Okay, so here I can assume that this direction is x direction, this direction is y direction, and this direction is the z direction. So I can say the antenna length is this much. So above I can say the antenna length is Z dash is equal to L by 2, and here Z is equal to minus L by 2. This is nothing but the, I can say, dz dash, and this particular is say Z dash. Now my observation point here is nothing but this one, and I can say this distance is nothing but the distance r. This is the radius r, you can say, and this is angle theta. So if I am going to analyze this particular antenna, or if this particular is nothing but the current distribution of this particular antenna, how I am going to find out the things for this particular small dipole antenna? So I'll write here the current distribution. This is nothing but the small dipole antenna, minus L by 2 to L by 2. So when I'm talking about the current distribution on this particular dipole antenna, I can say this is nothing but the current distribution, whereas I'm assuming this is my small dipole antenna. This is the current, whereas I0 is the maximum current, and it decreases like this. So the distribution of the current is nothing but the triangular distribution over here. So Z is equal to 0. Here Z is equal to L by 2. Here Z is equal to minus L by 2. And this distribution will be I0 1 plus 2 by L Z dash. Maximum will be at the center, and again you can say this is I0 1 minus 2 by L Z dash. So this is nothing but the meaning which we have seen here in the previous expression. So this I can say is nothing but the current distribution on a small dipole. So similarly we have expressed this current distributions over here from 0 to L by 2. So from 0 to L by 2, you can see here this current distribution is nothing but the I0 1 minus 2 by L Z dash, whereas in the below part you can say from minus L by 2 to 0, I'll have a I0 1 plus 2 by L is Z dash AZ dash. So this is nothing but the current distribution on the small dipole. Now we'll go step by step. So the first step is here, as we have already discussed the 4 steps how we can find out how we can analyze the antenna. Our step first is nothing but we are going to find out the vector magnetic potential first. So let us find out the vector magnetic potential for this particular antenna. So whenever we are talking about the vector magnetic potential, so this is step 1. To find the vector magnetic potential A bar. So while calculating A bar, we have an expression for the vector magnetic potential due to small current element, that is dl. So dA bar is equal to mu I bar dl 4 pi r e raised to minus j k r. Now for small section along with the z axis, you can say dl is equal to dz. So for small section, I can write that dl is equal to dz bar. So here we can say that our A bar is equal to AZ bar. So then we can write here D AZ bar is equal to mu I AZ bar divided by 4 pi r dz dash e raised to minus j k r. Now let us solve this particular equation further, or I can write this particular equation d AZ is equal to mu I 4 pi r e raised to minus j k r dz dash. Now integrating, here I have got dAz is equal to mu I 4 pi r e raised to minus j k r dz dash. So integrating dAz within limits from z is equal to minus L by 2 to L by 2. I am integrating this particular equation. So here I'll get, by integration I'll get this equation like this. So AZ is equal to minus L by 2 L by 2 d a z. Now let us integrate this particular equation. So but the current is not same over the entire length. If I am assuming the current, my current will not be same for the entire length, so I need to assume over here for the lower half and the upper half the currents are different, so you need to split this equation. So az is equal to mu by 4 pi minus L by 2 to 0. I have a different current, that is I0 1 minus 2 by L z dash e raised to minus jkr by r z dash plus. Now if I see the another integration or another you can say current distribution, it will be 0 to L by 2, and this will be I0, here it will be minus L by 2, it will be 0 to L by 2, this will be 1 plus 2 by L z dash e raised to minus jkr divided by r dz dash. So I have integrated with respect to two integrations. Now two limits I have to put over here as the current is not same. Now here we know that we are talking about the small dipole antenna, so L is nothing but the greater than, I can say lambda by 50, but it is less than lambda by, I can say 10 over here. So here the difference between RR is very small. So for this antenna, so you can say that your difference between R and R, the difference will be very small. I can write difference will be very small and can be neglected. So this is valid for every R which is appealing alone as a distance or coming with the phase constant k. So for a small dipole, the maximum length L is equal to lambda by 10. The difference between R and R will be very small. So I can say the path difference here is equal to R minus R, which is nothing but the L by 2 cos of theta, which is nothing but the lambda by 2 cos of theta. So here the path difference, if you calculate here, the path difference is equal to k r minus r k lambda by 20 cos of theta, and that's why if you simplify it further you will get it 2 pi by lambda, as I have put the value of phase constant 2 pi by lambda. This will be lambda by 20 cos of theta, which is pi by 10 cos of theta. So here I have got the phase difference is nothing but the, so here I have calculated the path difference and here I have calculated the phase difference. So phase difference is k into r minus r, which is nothing but the lambda by 10 cos theta. So the maximum phase difference is pi by 18. So I can say here maximum phase difference is equal to pi by 10, which is nothing but the 180 by 10, which is nothing but the 18 degree, and it is very small, hence can be neglected. So here we can neglect this particular phase difference. So if we neglect this phase difference, the above equation which we have calculated previously, we can write that equation like this. So here the equation will become Az is equal to mu I0 4 pi r e raised to minus jkr L by 2 to 0 1 minus 2 by L z dash with respect to dz bar plus 0 to L by 2. This will be the minus and that will be the 0 to L by 2. This will be 1 plus 2 by L z dash dz dash. So solving it further, I'll write mu I0 4 pi r e raised to minus jkr. Take the limits here. So z dash minus 2 by L z dash square 2 raised to 0 to minus L by 2 plus z dash plus 2 by L z dash square by 2 L by 2 to 0. So when you solve this particular equation further, you will get it mu I0 4 pi r e raised to minus j k r. This will be L by 2 minus L by 4 plus, I'll write this L by 2 minus L by 4. So again solving this equation, I'll get AZ is equal to 1 by 2 mu I0L divided by 4 pi r e raised to minus jkr. Now here we can see the term 1/2 is kept out in the expression purposely because the remaining expression is same as that of the AZ for infinitesimal dipole. If you to remember, this is the same as the infinitesimal dipole as that of the AZ for infinitesimal dipole. Then we can say AZ for small dipole is half of the AZ of the infinitesimal dipole. So for small dipole, the only difference is that whatever vector magnetic potential is there for the infinitesimal dipole, for small dipole it will be the half. Now next one is nothing but we have find out the vector magnetic potential. The second step here is to find the magnetic field intensity. So let us solve, or let us find out the magnetic field intensity. So step 2, to find magnetic field intensity, which is nothing but the H bar. Now here, while solving this particular, we know that B bar is equal to mu H bar, which is nothing but the del cross of A bar. Okay, so mu H bar is equal to 1 upon r square sine theta AR r A theta r sine theta A5 d by dr d by d theta, and I can say this is nothing but the d by d5. This is AR r A theta r sine theta and A5. Now let us solve this particular equation further to get the magnetic field intensity. So here, using AZ component, we can obtain AR, A theta, A5. So these relations are similar to infinitesimal dipole given by, so you can say AR is equal to AZ cos of theta, A theta is equal to minus AZ sine of theta, and A5 is equal to 0. So since the current filament is placed along with the z-axis, there is a cylindrical symmetry giving AZ independent of 5. Okay? And that's why this results in d by d5 is equal to 0. Okay? So using the equation, previous equation, we can write this is equal to 0, and you can write this A5 is also equal to 0. So further solving this equation, we can write here. Further, if you solve this particular equations and putting all those values zeros, which we have concluded previously in the equation, so here mu H bar is equal to 1 upon r square sine theta AR bar. I'll write this is nothing but the r A theta bar r sine theta A5 bar d by dr d by d theta, d by d5 is 0, that's why I write it 0, AZ cos of theta minus r AZ sine of theta, and this will be 0. So this is nothing but the mu H bar. Now I'm going to resolve this particular in r theta and phi direction for this H component. Okay? So 1 upon r0 first, solve this one, and then we will resolve sine theta. Here I can write r sine A of phi d by dr minus r AZ sine theta minus d by d theta AZ cos of theta. The right hand side have only A phi component, and the left hand side will have only H phi component for H. Okay? So I can write here, you will write the right hand side will have only A5 component and left hand side will have only H5 components. So mu H5 is equal to 1 upon R d by dr minus R Az sine of theta minus 1 by R d by d theta Az cos of theta. So further solving this particular equation, note that the component Az is inversely proportional to R. You can see here your Az component is inversely proportional to R. So if we refer the previous equation, so RAZ will have R term in the denominator. So you can write, after differentiating with respect to R, we can multiply it by 1 by R. Okay, so then the first term on the RHS will have R term in the denominator, that is first term is inversely proportional to R. So applying similar logic to the second term, we find the term is inversely proportional to R square. So in far field region, so if I talk about the far field region, we can say in far field region KR is greater than 1. So the second term will be very small as compared to the first term. Okay, so this is 1 by R d by dr minus R Az sine theta 1 by R d by d Az cos theta. So here the second term will be very small as compared to the first term and can be neglected. So here I can write mu H5 is equal to 1 by R d by dr minus R Az sine of theta. Okay, so we have put it only Az over here, but we have calculated Az in the step number 1. So we can put the value of Az in this particular equation. So putting the values of Az, mu H5 can be written. So mu H5 is equal to minus 1 by R 1 by 2 mu I0L 4 pi sine of theta d by dr e raised to minus jkr. So further solving this particular equation, I'll get 1 by 2 j k mu I0L 4 pi r sine theta e raised to minus jkr, or you can write H5 is equal to 1 by 2 j k I0L 4 pi r sine theta e raised to minus jkr a per m. So this is nothing but the solution for H5. So this is the required expression for H5 for the small dipole antenna. Now the value is exactly half of the H5 for the infinitesimal dipole in the far field region. Now let us talk about the third step, which says that you need to find out here electric field. So to find electric field intensity, so how we can find out the electric field intensity if we have got magnetic field intensity in the phi direction. So let us solve this particular step number 3. So from the infinitesimal dipole analysis, we know that in the far field region the component ER is 0. The electric field E will have only E theta component. Now E theta can be obtained by the H5 component. Okay, so here we can calculate E theta by H5 is equal to neta, which is nothing but the 120 pi. This is for free space, which is also called as the intrinsic impedance. So we have got H5 over here, and for infinitesimal dipole analysis we know that we will have only E theta component. So here E theta is equal to neta into H5. So this will be 1 by 2 neta k I0L divided by 4 pi r sine theta. You can say this will be volts per meters. So this is nothing but the E theta for small dipole antennas. Now as we have got E theta, the last step is nothing but how we can find out the radiation resistance. So let us talk about the radiation resistance for the small dipole. So step number 4, to obtain RR, which is nothing but the radiation resistance. So to find out the radiation resistance, we proceed similar to lambda by 2 dipole. The average power density, now we know that average power density is equal to 1/2 real components E into H complex, which is nothing but the 1/2 E theta A theta into H5 complex A5. So 1/2 E theta A theta bar into, I'll resolve this H5, E theta complex divided by N A5. So solving it further, I'll get 1/2 RE E theta square pi neta into AR. As we know that A theta into or A theta cross A5 results into AR. So we have put it that things over there. Now to solve this particular equation further, we'll assume here I can say let A is equal to X plus JY, then A complex is equal to X minus JY, and A into A complex will be X plus JY, X minus JY, which is equal to X square plus Y square. Now but here mod of A is nothing but the X square plus Y square. So here I can write A into A complex is equal to X square plus Y square square, or I can write A into A complex is equal to mod A square. Okay, so putting that things over there in the equation, we can write here. So here we can write W average is equal to 1/2 neta E theta square AR watts per meter square. So the power radiated is obtained by integrating W average over the closed surface. So I can write here P radiated is equal to surface integration of this power density with respect to ds. So I'll write here it will be 0 to 2 pi, 5 is equal to 0 to 2 pi, theta is equal to 0 to pi, 1/2 neta E theta square AR R square sine theta d theta d5 AR. So after integrating this particular equation, I can write this is nothing but the 1/2 neta 0 to 2 pi 0 to pi n k I0 L theta pi r sine theta square r square sine theta d theta d5. So further solving this equation, I can write here this is nothing but the 15/4 pi I0 L pi lambda square. 5 varies from 0 to 2 pi. It will be 0 to pi sine cube of theta d theta. Okay, so here k is nothing but the 2 pi by lambda and n is nothing but the 125. So we know that k is phase constant 2 pi by lambda and neta is 120 pi. So the integral on LHS we have already solved lambda by, we have already solved the left hand side over here, so that will be 4 by 3. So if you will put these things 4 by 3 over there, your radiated power will be P radiated here is equal to 15 by 4 pi I0 square L by lambda square into 2 pi, and this value is nothing but the 4 by 3. So further solving it gets 10 pi square I0 square L by lambda square. So the power radiated can also be written in terms of RR. So here if you are going to write down the term this in the radiation resistance, you can write this particular term in this particular equation. So here you are having this particular radiated power 10 pi square I0. So if I write this particular term in terms of the, I can say RR, so this particular equation will become now 1 half I0 square RR is equal to 10 pi square I0 square L by lambda square. So RR is equal to 20 pi square L by lambda square, and as this is the resistance, the unit will be the ohm over here. Now the value of 1 by 4 of the obtained infinitesimal dipole is nothing but the, so this is the radiation resistance. So to find directivity, T is equal to 4 pi U max by P radiated. So U is equal to R square W average, which is nothing but the R square. You can write it here, E square to neta, R square to neta, 1 half neta KI0L by 4 pi R square. So further solving this particular equation, I can write this is equal to R square 2 neta, neta by 2 pi by lambda I0L sine of theta divided by 4 pi R square, which comes n by 32 I0 square L by lambda square sine square theta. Now here U max will be n by 32 I0 square lambda square, where I am assuming that sine square theta will be 1 to get the U max. So this is the maximum value of the radiation intensity. So I can say I'll get this when my theta is equal to pi by 2. Now let us talk about the radiated power, as we are calculating this for the radiated power. So I'll write here P radiated is equal to 10 pi square I0 square L by lambda square. So I can write this is my radiated power. So to find out the directivity over here, so D is equal to, for this, T is equal to 4 pi U max by P radiated. Now this comes n by 32 I0 square L by lambda square divided by, this is 4 pi, 10 pi square I0 square L by lambda square, which comes 1.5. So here the directivity is nothing but the 1.5. So if we talk about the radiation pattern, how we are going to find out the radiation pattern, we can put the values here, different values here for the theta, and then we can get the radiation pattern. So to find radiation pattern, change the values of theta So this is theta is equal to 0, this is theta is equal to 90, and you're placing your dipole somewhere here. So this is my dipole. I have placed my dipole over here. So I can say the radiation pattern for this particular small dipole will be like this. So this is nothing but the dipole. So I can see the radiation pattern will be like this. So we can say, since E theta is directly proportional to the sine theta, so the radiation pattern will have the figure of 8 here, whereas you will find the maximum radiation at theta is equal to 90 degree, and you can say the maximum radiations will be at 270 degree. So this is all about the small dipole antenna. We'll stop here. Thank you.